Good afternoon. I'm Zbigniew Drogosz, and I'm going to talk about loop-based observables in four-dimensional causal dynamical triangulations. In the previous talk, Professor Ambjorn gave a short introduction to the CDT, but I'm going to review a few most important points. So, general relativity is a perturbatively non-renormalizable theory, field theory. The gravitational constant G has a mass dimension of -2, which is lesser than 0, but still this theory can be analyzed by using numerical computer simulations of the lattice theory. So we can discretize the space-time, build it out of simplices, and use the Redge prescription, the Redge calculus, in which the curvature is determined by the deficit angles around d-2 simplices, and the action on a simplicial manifold in Redge calculus has a very simple form, also mentioned by the previous speaker. And here we have three coupling constants. One of them plays the role of 1 over g, another one plays the role of the cosmological constant lambda, and we have simple parameters n0. This is the total number of zero-dimensional simplices, so the vertices. The total number, and for the total number of four-dimensional simplices in the case of four-dimensional CDT, of course, and the number of 4-1 simplices, which is a subset of all n4 simplices. And I will show them more on the next slide. And we want to quantize the theory, so we use Feynman path integral. And if it were a quantum mechanics of one particle, then we would integrate over all paths of the particle. But here we integrate over all possible configurations of the gravitational fields. So over all possible geometries of the spacetime. And in this discretized case, this is a sum, the discrete sum over all triangulations. And we are interested in causal dynamical triangulations. And what does it mean? The word causal means that there's no causality violations. So no change in the spatial topology of the universe. And this means that this topology of the whole spacetime can be rewritten as a Cartesian product of spatial manifold and time interval, and so we have a proper time foliation, and this leads to the fact that we have only two basic kind of four simplices. We can either have four vertices on one time slice and one vertex on another time slice, or three vertices on one time slice and two vertices on another time slice. So these are 4-1 and 3-2 simplices. And the triangulations are also dynamical, which means that the shape of the lattice is not constant. This is not a regular lattice, but what is constant is the length of the time-like edges and of the space-like edges, and but the total number of simplices and the connection between them can change. And this theory can be solved analytically in 1+1 dimensions, but in higher dimensions, there is no analytical solution, so we have to use computer Monte Carlo simulations. And these are performed in such a way that we start from a very simple configuration with a topology of our choice, and then we let it evolve by means of randomly chosen moves of 7 types, which moves have the properties that they firstly preserve the topology and the causality. Secondly, they are ergodic, which means that we can get from any configuration with a given topology to any other configuration with the same topology by a finite series of moves. And also the third property is that the moves keep the so-called detailed balance condition, which basically means that they are made with a correct probability, so that the probability of obtaining any configuration and triangulation is correct and consistent with the action. So this is the introduction, and if we choose the spatial topology to be that of a free torus, so the Cartesian product of three circles. Then, depending on the coupling constants, the configuration will be in one of four phases, and the talk will be about the properties of generic configuration in the C phase, which is considered to be the most physical one. Okay, there's a lot of research about the phase transition and so on in many articles about CDT. So we want to use loops, but how to measure the winding numbers or how to construct loops with winding numbers that we want. So, this is not so simple, because on the computer the triangulations are encoded basically as a graph. We have a list of simplices and all the connections between the simplices. And this is not easy to give a winding number of a loop in a graph. So to make it simpler, we introduce additional structures, which are the fictitious barriers. So they are basically the boundaries of an elementary cell. If we consider the torus, because what we have in this case is actually four-dimensional torus, because we treat the time dimension also as a circle for technical reasons. Then, if we consider this as an infinite periodic system, then this is just one elementary cell repeated infinitely many times in each direction. And then the loop of a non-trivial winding numbers is just a path connecting a simplex to its copy in another elementary cell. And now, with those barriers, if we want to measure the winding numbers of such a loop, then we just count the number of times the loop passes through those barriers. And each loop will have four independent winding numbers, because this torus is topologically a Cartesian product of four circles. And those barriers would also be very difficult to introduce to a complicated configuration. So we add them at the beginning of the simulation, when we start from such a simple configuration, which is built out of hypercubes, which are triangularized, and then we just keep track of the barriers throughout our simulations. And the barriers are fictitious in the sense that there is no term in the action that depends on their position. Okay, so and we keep track of their position, and we don't let them be destroyed, or don't let their properties be worsened throughout our algorithm. Yes, so now we have those barriers, and what can we measure? First of all, we can for each simplex we can measure the shortest the length of the shortest loop that starts at a given simplex. So this is the algorithm is very simple. We choose one simplex, and then we make a spherical diffusion wave. So in the first step, we mark the neighbors of this chosen simplex. In the second step, we mark the neighbors of the simplices that we reached during the first step. And in the third step, we mark the neighbors of those, and so on. And after a number of steps, we will ultimately get to the copy of the simplex, because we consider the torus again as a infinite periodic system. And now we can perform these measurements for each simplex in the configuration. And our configuration had the configuration that we analyzed had more than 370,000 simplices, and those shortest loop lengths in a given direction, we can also call them heights of the simplex. And for example, let's look at this histogram. The blue, green, and the orange line are the heights in the three spatial directions. So the the length of the shortest loops passing through all simplices. And we can see that this tells us that the structure of the simplice is pretty complicated. For example, if it were just a regular rectangular lattice, then, for example, it could be that for every simplex, the height in a given direction would just have one value the same for all simplices. But here we have the whole distribution, and also interestingly, well, first of all, the shapes for all directions are very similar, and also there are very strong correlations. If we make a plot with a two-dimensional histogram with heights in two different directions, then we see that they are very strongly correlated. And so how to explain this shape of those plots? Well, the configuration has a shape that must be a bit like this, which with a pretty small classical region, let's call this semi-classical region, close to the hole, and a lot of outgrowth of complicated fractal structure. So this could be interpreted as quantum fluctuations. And the greatest part of all the simplices in the configuration lies within those outgrowths. And now the correlation is easy to understand, because if you want to, if we start at a simplex within such an outgrowth, and we want to make a loop in any direction, then first we have to make a number of steps to leave such an outgrowth, and then we have to make a loop, and then we have to go back into the outgrowth. So no matter in what direction we want the loop to be, we still have to make a number of steps here within such an outgrowth. So this tells us something about the general shape of the configuration. And we can also look at the neighborhood of simplices in those, let's call it semi-classical and quantum regions. So if we start at a simplex in the semi-classical region, this is the central simplex of height 18 in the x direction, and we draw a graph of 5 shells, concentric shells around this simplex. So this is a graph of a dual lattice. So here, each simplex of the triangulation is represented as a vertex of this graph, and the interfaces between simplices are the connections between vertices. So here we see that this graph around this in this semi-classical region is pretty irregular. It's almost tree-like. And now let's compare it with a graph in this outgrowth region. So here the numbers within those circles are the heights of simplices. So we start from a simplex with height 55. And these are actually 6 shells, not even 5. And we can see that the total number of simplices is very much lower, even though this is even more layers, so it should be even several times more simplices than the previous one if the structure were the same. And so we can see that here it is not so tree-like. There's a lot of loops here. The simplices are very much interconnected, and also this smaller growth of the number of simplices as we go consecutive steps from the starting simplex means also that the Hausdorff dimension in such a region is smaller. The Hausdorff dimension in this semi-classical region must be about 4, whereas here it is lesser than 3. So we can see first of all that the height of the simplex tells us something about its position within the configuration. It's not like a coordinate, but also tells us something about its position. We can also look at the loops of high winding numbers, and here the results are pretty easy to understand. That if we look for a loop of winding number n000, and subtract from its length the length of the loop of winding number n-1, 0, 0, 0, then for n that is large enough, this difference is going to be just the length of the shortest path within the whole configuration, of the shortest loop within the whole configuration. So, for example, if we start at a simplex within an outgrowth and we just make one loop, then it's something like it's some loop. But if we want to find a loop with winding number 2, then perhaps it's more efficient to go towards a narrower section of a torus and then make two loops around it and go back. And if for large enough n, it's optimal to go to the most narrow section of the torus, to go to the loop of minimal length, and then use it n times, and then go back to the starting simplex, no matter where the starting simplex was. And this is shown on this plot also. So for a loop of winding number 1, the heights of the simplexes that we meet along the path go back to 20 something, for to about 20, and for winding number 3, 0, 0, 0, we are already using the shortest path in the configuration. However, if we do the same, but searching not for loops of winding number n0, 0, 0, but with winding numbers n, a, b, c, when a, b, c are n numbers that we don't care about, we care only about n, then it turns out that we find even shorter loops, even shorter than the shortest loops in the elementary directions. So, for example, the shortest loop of winding numbers 1, 0, 0, 0 has a length 18, but there is a loop of winding numbers 1, -1, 1, the smaller length, and there's even a loop of winding numbers 2, -1, 1, with a length 27, which is much less than twice 18. Right, so this tells us that the torus is also not rectangular, it's twisted or skewed in some way, so that the shortest path goes askew, goes in some non-cardinal direction. And the last measurement that I want to present is one of the most interesting ones, is the number of shortest loops passing through simplexes. For each simplex, we can find not only the length of the shortest loop that go through it, but we can also write this shortest loop down and get a list of simplexes through which this loop passes. And we can do this for every simplex in the configuration, and then we get about more than 370,000 lists. And then we can count the number of occurrences of each simplex in all those lists. And we find out that there are some simplexes for which the total number of occurrences is several tens of thousands of times. And there are some simplexes which have hardly any occurrences. And so these simplexes that are more popular, so to speak, would be the simplexes in the semi-classical part. And this means also that the geodesics tend to go along this semi-classical part and tend to avoid the quantum fluctuation region. And now if we make such a log-log histogram, where on the x-axis we have the number of paths that go along a simplex, and on the y-axis we have the number of simplexes with this property, then it turns out that we can fit very well a power law to this, and the exponent seems to be -2. Here, very close to -2, and this seems to be meaningful because this exponent is so nice. And now we are looking for a simple model of how to construct a graph with such a property, that the number of vertices through which the shortest certain number of shortest path goes is like this. It's proportional to the number of paths to the power -2. And it seems that there must exist some elegant explanation. Yes, so this was all that I had to say today. So to summarize, the loop lengths tell us something about the local and global properties of a generic configuration. And the typical configuration has a small semi-classical region, and whereas the most greatest part of the synthesis are building the large quantum fractal outgrowths, and also analyzing some more complicated properties, so some more complicated observables might shed some light on the properties of the configuration, might explain how they constructed and to what kind of graphs they are similar. Okay, so thank you for your attention. That's all.
Well, we would like to thank the speaker. Do we have some questions or comments to this talk? Yes, Daniel, I think, did you ask?
Yes, I would like to ask if is it possible that this power law exponent will be much different in different points of the phase structure, or the phase space?
Yes, the same calculation might be performed also in the other phases. We just have to start the simulations there and analyze those generic configurations in those phases. And indeed, seems to me that the exponent should be different because the general shape of the configuration in the different phase is different. Some of them, for example, are like branch polymers or are like crumpled phase. So I think that yes, that this exponent is -2 only for the C phase.